I'm about to show you a machine that makes electricity at 3 in the morning, in the rain, in January, when there is not a single photon of sunlight anywhere near your property, and every solar panel on your roof is producing exactly nothing. It can be built out of a junkyard car alternator, a length of plastic pipe, and a wheel you can make from spoons. People run their whole homes on them, and 100 years ago, there were tens of thousands of them scattered across this country, on farms, at mills, behind small towns, quietly making their own power without asking anyone's permission. Today, almost nobody knows they exist. This is microhydro, and I'm going to be straight with you from the very first minute, because this video has a catch, and I'd rather you hear it now than 5 minutes in. This only works if you have running water with a drop on or beside your land, a creek, a stream, a spring line, a ditch coming down a hillside. If your property is flat and dry, this is a fascinating video, and it is not going to power your house. I'm not going to pretend otherwise, because half the internet will. But if you do have water, or you're looking at land, or you have a family property with a creek on it, then what I'm about to show you is genuinely the best-kept secret in off-grid power. Because per dollar spent in the right spot, nothing on Earth beats it. Not solar, not wind, nothing. Stay with me, because by the end you'll know exactly why it outproduces solar so badly, it's almost embarrassing. How to measure your own water in about 20 minutes with a garden hose and a bucket. What parts you can pull from a scrapyard, and the honest, genuinely infuriating reason this technology vanished from a country that used to run on it. Let me start with the comparison, because the numbers here are not close. Everybody understands solar now. Panels on the roof, sunshine in, electricity out. It's brilliant technology, and it's gotten astonishingly cheap. But solar has one hard limitation nobody can engineer away, and it's this: the sun is not always up. Even in a good sunny location, a solar panel only produces meaningful power for a handful of hours a day. Clouds cut it, winter cuts it, night stops it dead, which means the actual electricity you harvest over a full day is a small fraction of what those panels are rated to produce. And to have power at night, you have to store it, which means batteries, which is where most of your money goes. Now, here's water. A stream does not care that it's dark. It does not care that it's cloudy, or December, or 3 in the morning. It runs at midnight exactly as it runs at noon, which means a microhydro system doesn't produce power for a few hours a day. It produces power for 24, a very modest microhydro setup putting out a few hundred watts running continuously. Generates more electricity in a day than a solar array several times its rating. It just does it slowly and steadily instead of in a midday burst. And because it never stops, you need dramatically less battery storage. You're not saving up for a 14-hour blackout every single night. That is the entire game. Solar sprints and then sleeps. Water jogs forever. And let me make that concrete, because a few hundred watts sounds small until you understand what continuous means. A load that runs all the time, your refrigerator, cycling lights, a router, chargers, a well pump, a freezer, is exactly the kind of load a steady trickle of power handles beautifully, because the battery bank is being refilled every minute of every hour, including while you sleep. What continuous power struggles with is the big short spike, an electric kettle, a hairdryer, a welder. But that's what a battery bank and inverter are for. The hydro quietly fills the tank around the clock, and you draw the spike out of the tank when you need it. Plenty of homes run entirely this way, and the owners will tell you the strangest part is how boring it becomes. There's no watching the weather. There's no rationing on a cloudy week. It's just on. And here's the part that surprises people most. It doesn't take much water. You do not need a river. You do not need a waterfall. A stream you could step across, with enough drop, can run a house. So let me explain how the thing actually works. Because once you understand the two numbers involved, everything else makes sense. Microhydro power comes down to two things: head and flow. Head is the vertical drop, how far the water falls from where you take it in to where your generator sits. Flow is how much water is moving, usually measured in gallons per minute. Multiply them together, and you have your power potential. That's it. That's the whole physics. And this is the important insight. You can trade one for the other. A tiny trickle falling a long way down a steep hillside can produce serious power. A larger, lazier flow with only a few feet of drop can produce the same. High head and low flow, Or low head and high flow both work. They just need different equipment. Which is why so many properties that people assume are useless turn out to have real potential. And why so many people with a perfectly good stream have never once thought to measure it. So let me tell you how to measure yours, because you can do this today for free. For flow, take a bucket of known size. A 5-gallon bucket is perfect, and find or make a spot where the whole stream funnels through one point. Time how many seconds it takes to fill the bucket. If it fills in 10 seconds, you've got 30 gallons a minute. Do it a few times and average it. That's your flow, and it's genuinely that simple. For head, you're measuring vertical drop, not distance along the ground. The old cheap method is a length of clear hose filled with water. Run it downhill. And because water finds its own level, you can leapfrog your way down the slope, measuring the drop in stages. A builder's level and a stick works too, and these days, a decent phone app or a laser level makes it faster. What you want is the total vertical fall between where you'd put your intake upstream and where you'd put your generator downstream. Get those two numbers, and you can work out roughly what your site is capable of. There are free calculators for it, but the rule of thumb is straightforward. More drop and more water means more power. And a surprisingly ordinary creek with 20 or 30 feet of fall over a reasonable distance can produce a genuinely useful continuous supply. Now, the machine itself, and this is where the scrapyard comes in. A microhydro system has 4 parts. An intake, where you take water from the stream, usually a screened box or a small pool, so you're pulling clean water and not leaves and gravel. A penstock, which is just the pipe carrying that water downhill. Plastic pipe is standard and cheap, and that pipe matters more than beginners expect. Water rubbing against pipe walls loses energy the whole way down. Engineers call it friction loss, and a pipe that's too narrow or too long can quietly eat a large share of the power you measured on paper. So the rule is, go bigger on the pipe than feels necessary. Keep the run as short and as straight as the ground allows, and avoid unnecessary bends. Undersizing the penstock to save money is probably the single most common mistake in home systems. And the frustrating part is that you can't see it. The machine simply underperforms, and you never quite know why. A turbine, which is the wheel the water hits, and a generator, which the wheel spins. The turbine you pick depends on your site. If you've got good height and modest water, you want a Pelton or Turgo wheel. That's a disc with cup-shaped buckets around the rim, hit by a high-speed jet of water from a nozzle. It looks almost comically simple, and it's brutally efficient. And here's the classic homebuilder's trick that's been passed around for decades. The buckets on a small Pelton wheel can be made from ordinary metal spoons, cut and fixed around a hub. That's not a joke, and it's not a myth. Working wheels have been built exactly that way, if instead you have lots of water and very little drop. You want something more like a propeller or a paddle wheel that catches the volume rather than the speed. For the generator, the Scrapyard Classic is a car alternator. They're everywhere, they're cheap, they're built to spin for years, and they produce the low-voltage direct current that charges a battery bank, which is exactly what an off-grid system wants. Permanent magnet motors are also popular, and a lot of builders use motors salvaged from old treadmills, which run beautifully as generators when you spin them backwards. None of this is exotic. The whole thing is a wheel, a shaft, and a spinning magnet, and people have been building versions of it for over a century. Add a charge controller, a small battery bank, and an inverter, and you have a power plant that fits in a shed and never stops. And the cost picture is where this gets genuinely hard to argue with. A scrap-built system, salvaged alternator, plastic pipe, a homemade wheel, and second-hand electrical gear can come in at a few $100s for someone willing to do the work. Even a professionally made turbine and generator for a small home system typically costs a fraction of the panel and battery array you'd need to produce. The same electricity over a full day, precisely because you're not paying to store 14 hours of darkness every single night. The batteries are usually the most expensive part of any off-grid system, and continuous generation is the one thing that shrinks them. The expensive part of microhydro, ironically, is almost never the machine. It's the pipe, the trenching, and as you'll see in a minute, the paperwork. Now, the question in the title, why did this vanish? And I'm not going to hand you a story about hidden blueprints and secret suppression, because that's not what happened. And the truth is more interesting and, frankly, more annoying. Start with what we lost. A century ago, this country ran on falling water. Tens of thousands of small water-powered mills and workshops dotted the landscape, grinding grain, sawing lumber, running machinery. As electricity arrived, many of those same sites were converted to generate it, and small hydro plants powered individual farms, factories, and whole small towns. If you had a creek with a drop, you had power, and you owned it. Independent, local, unglamorous, and everywhere. And that wasn't a fringe practice, it was the backbone of how things got made. Before steam, and long before the grid, if you wanted to grind flour, saw boards, full cloth, or hammer iron, you built beside falling water, because falling water was the only reliable mode of power there was. That's why so many old towns sit exactly where they do. Somebody found a drop in a creek and built a mill, and a village grew around it. Look at the place names near you. Mill Creek, Millbrook, Mill Road. Those aren't decorative. They're a map of where the power used to be. When electricity arrived, the obvious move was simply to bolt a generator onto machinery that was already spinning. And for a few decades, a great many rural communities lit their homes with the same water that had ground their grain. Then the grid came. Rural electrification in the 1930s was a genuinely transformative program that ran power lines to farms and communities that had none. And it worked. But it also meant that suddenly, plugging into a wire was easier than maintaining your own turbine. At the same time, enormous centralized power stations burning cheap coal and oil could produce electricity at a price no small operator could touch. So one by one, the little water plants shut down. Not because they stopped working, many of them physically still exist, dams and all, but because it became easier and cheaper to buy power than to make it. That's not a conspiracy. That's economics. And it's how almost every self-sufficient technology in this country died. But here's the part that actually deserves the word buried, and it's the modern part. Today, if you own land with a stream and you want to install a small turbine, the biggest obstacle you'll face is not the equipment and not the engineering. It's paperwork. In much of the country, and especially in the West, water rights are complicated legal property. The water crossing your land is very often not simply yours to divert. Depending on where you live, you may need permits from state agencies for the diversion, environmental review for the impact on the stream, approvals concerning fish passage, and in some cases, a federal exemption. People routinely discover that the studies and the permits cost more than the entire generator, penstock, and turbine put together. So no, nobody drove out and cut anyone's wires. What happened is that we built a system in which centralized, metered power is effortless, and independent generation is a legal project. The technology was never hidden. It was simply made inconvenient enough that almost nobody bothers, which, if you think about it, is a far more effective way to bury something than hiding a blueprint. Now let me be honest about the limits, because I said I would. The first one, I've already told you, and I'll say it again, because it's the one that matters. You need water with drop. No stream, no drop, no microhydro. A flat pond does nothing. A rain barrel does nothing. Physics is not negotiable here. Second, streams change. The flow you measure in April after snowmelt is not the flow you'll have in August, and you have to size your system around your dry season, not your best week. And when a real storm comes through, your intake needs to survive debris, gravel, and a stream that's suddenly 10 times its normal size. Anyone who's run one of these will tell you the same thing. The machine is reliable, but keeping leaves and silt out of the intake is the actual job. Third, the legal side is not optional. Do not dam or divert a stream you don't have the right to touch. Check your state's water rights rules and talk to your local authority before you dig anything. This is the single most common way home projects turn into expensive problems, and it's entirely avoidable by making a couple of phone calls first. Fourth, safety, and I want to be direct about this. You are combining water and electricity, which demands respect. Every electrical component needs to be in a properly rated, sealed enclosure above flood level and correctly grounded. Battery banks are not toys. A large battery can deliver enormous current, so it needs proper fusing, correct cable sizing, and ventilation. And you never, ever connect a home-built generator into your house wiring in a way that could push power back onto the utility lines. Backfeeding a grid can kill a lineman working on what he believes is a dead circuit. If you're tying into a house that is a job for a qualified electrician and the proper transfer equipment, there's no shortcut worth taking here. And one technical point that's specific to hydro and catches solar people off guard. With solar, when your batteries are full, the controller simply stops taking power from the panels and nothing bad happens. You can't do that with water. The stream keeps pushing, the wheel keeps turning, and if you abruptly disconnect the load, the generator can spin up far faster than it was designed to. That's why hydro systems use what's called a diversion or dump load. Instead of switching the generator off, the controller sends the surplus somewhere harmless, most often a water heating element or a resistor bank. So the machine always has something to push against. It's a small detail, and it's the difference between a system that runs for decades and one that destroys itself the first week. The batteries fill up. A lot of people heat their domestic water with that surplus, which turns a safety requirement into a free hot shower. And fifth, be a decent neighbor to the stream. A microhydro system takes water out at one point and gives it back at another. And done properly, it's about as gentle as energy generation gets. Done carelessly, it dewaters a stretch of creek and blocks fish. Screen your intake, leave enough water in the stream bed, and return what you borrowed. Let me tell you what got me interested in this. A friend of mine bought a scruffy piece of hill land with a creek running down one side, and he did what most people do, which is look into solar. Then an old-timer walked the property with him, stood next to that creek, and asked how far it dropped. Nobody had ever thought to ask. They measured it with a hose and a stick over one afternoon, a modest little creek, maybe a couple of feet across, dropping something like 30 feet down the slope. And that afternoon of measuring turned out to be worth more than every solar quote he'd collected, because that unremarkable trickle, running day and night, was capable of producing more electricity over a full day than the panel array. He'd been pricing with a fraction of the batteries because it never stopped. He'd owned that creek for a year and looked straight past it, the way we all do, because we've been taught that power comes from a panel or a pole. Let me answer the questions I know are coming. How much power can I actually get? It depends entirely on your head and flow. Measure both first, then run the numbers, and don't let anyone quote you a wattage before you've measured. Do I need a dam? Usually no, and often you don't want one. Most small systems use a simple screened intake and a pipe, which is far easier legally and far kinder to the stream. Does it really run at night? Yes, and that's the whole point, continuously, which is why it beats solar so decisively over a full day. Can I really use a car alternator? Yes, it's the classic starter build. Though purpose-made permanent magnet generators are more efficient if you want to go further. What about winter? Does it freeze? In cold climates, you have to manage ice at the intake and an exposed pipe. And it's one of the real maintenance challenges, but plenty of systems run right through northern winters. Do I need permission? Very likely, yes, depending on your state and your water rights check before you build. Can I combine it with solar? Absolutely, and it's a fantastic pairing. Hydro carries the steady base load day and night. Solar adds a surge in the sunniest months when streams often run lowest. How much maintenance is it? The generator is largely left alone. The intake is what needs regular attention, especially after storms and in leaf fall season. And what if my creek is small? Measure it before you dismiss it. Small creeks with good drop routinely outperform what people expect, and the only way to know is with a bucket and a hose. So here's the whole of it. There is a form of power generation that works at 3 in the morning in the rain, in the dead of winter, that produces steadily around the clock instead of in a midday burst, that needs far less battery storage as a result. And that can be built around a scrapyard alternator, a length of plastic pipe, and a wheel made of spoons. This country used to run on it, on tens of thousands of small sites, and then abandoned it, not because it stopped working, but because a wire from a distant power station became easier than maintaining your own machine. And because today, the permits often cost more than the hardware. If you have water with drop on your land, go measure it this weekend with a bucket and a hose. It costs you nothing. It takes an afternoon, and you may find out that the most valuable thing on your property is the little creek you've been walking past for years. So tell me down in the comments, do you have running water on your land, and have you ever measured the drop? And if you've built one of these, tell me what you're running off it, because I want to hear it. I read every single one. Next time I'm going to show you the pump that moves water uphill forever. No electricity, no fuel, no solar, no moving parts, but to valves. invented over 200 years ago and still running on farms today. Subscribe so you don't miss it. And remember, the people who came before us powered their lives with what was already moving past their front door.